Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We have looked at some of the basic topics of computer architecture. Topics that we have covered so far include looking at the instruction set, understanding the instruction set, instruction encoding, details of the arithmetic unit. We have looked at how integer and floating point operations can be carried out. We have looked at both. We have looked at all four operations: addition, subtraction, multiplication and division. So, what we will be covering in today's lecture would be the control unit. So, it is time for us to start looking at how the control unit is designed. Now, we know the various units that are required for doing the various computations, but we need to know how these different units can be controlled. So, we will be looking at how the CPU or the central processing unit or the control unit is designed. Remember that when we talk about designing the control unit, we need to make sure that we keep the performance of the entire machine in mind, because the control unit is you can look at it as the heart of the entire system. So, if the control unit is designed well, you can expect good performance. So, we will keep that in mind while we are designing the control unit. Now, coming to the different performance factors that we normally look at when you are designing the control unit. One factor that we consider is the instruction count, and these two other factors that we consider are the CPI and the cycle time. Now, instruction count basically is the number of instructions that would be required to execute a given program. Now, this would be normally determined by the instruction set architecture, that is the set of instructions that are made available, and the compiler. Remember, the compiler is the one that translates your high level code to the actual machine code. So, the compiler will have to choose the exact set of instructions so that the number of instructions to be executed are minimized. So, this factor of instruction count, that is number of instructions being minimum, is or being optimum, is determined by the ISA and the compiler. The other two factors which are important are CPI, which stands for clock cycles per instruction, that is the number of clock cycles that it takes for each instruction to be executed, and the cycle time, the clock cycle time. Okay, we know that everything is governed by the clock, so the cycle time is important. If your clock cycle time was very large, and even if you had fewer instructions, you will find that the total time taken would be very large. So, typically we say that the execution time of any given program will be the product of these three factors: instruction count, which is number of instructions in the program, into number of clock cycles per instruction, into the cycle time, the clock cycle time. So, this when you multiply these three factors, it will give you the total execution time. These are three factors that we need to remember, and these are three factors we try to optimize. So, if you reduce the three factors or even one of the three factors, it will help in reducing the number of the total execution time. Okay. So, now we will look at two different MIPS implementations to understand how these control unit can be designed. There are different ways in which the control unit can be designed. We will look at a very simple version first, and then we will look at a more realistic pipelined kind of an architecture. We will take a look at this simple version first. So, what we are going to do for understanding how the control unit can be designed is, we take a simple subset of instructions and we see how the control unit needs to be designed so that this subset of instructions can be executed correctly. Okay. So, the simple subset that we will consider will have the following instructions. We will have some memory reference instructions which will consist of a load and a store. So, LW will be a load word instruction, SW will be a store word instruction. And then we will also have arithmetic and logical instructions. We will consider an add, a subtract, an AND, an OR, and a shift left instruction. SLT stands for shift left. Then we will have also control transfer instructions. We will have a branch of equal, which is a conditional branch, and a jump, which is an unconditional branch. So, we are just looking at a small subset of instructions, and you will see how the control unit can be designed for this subset of instructions. Once we understand how this design needs to be done, then when we add other instructions or more complex instructions, we can accordingly design the control unit. So, let us look at the various factors that are involved in instruction execution. So, remember, we need to first fetch the instruction, then we decode the instruction, and then we execute the instruction, and then the results have to be written. Okay, these are the steps that are required. So, in order to execute these different steps, so what will be the factors that we need to consider? So, let us say for instance, we first of all start with accessing the instruction memory to fetch the instruction. So, what do we require for that? We normally said we use something called a program counter, a special register called the program counter, which will be used to point to the instruction memory so that the instruction can be fetched. Now, once we fetch the instructions will have information about which registers have to be accessed for reading the data and so on. So, register numbers are important. So, we need to read the register numbers and these will point to the register file. So, we will have a set of registers. So, a register file will be there and register numbers will point to which register out of that file you are going to read. And then depending on the instruction class, we just saw that we can have a memory reference instruction, or we can have an ALU instruction, or we can have a control transfer instruction. So, depending on the instruction class, we need to see what information we need. So, if you look at the instruction class, let us say it is an execution instruction. We just saw that we have some arithmetic and logic instructions. So, depending on the instruction, if it is an arithmetic instruction, you will get the data from the registers and the arithmetic result will have to be stored. If it is either a memory instruction or a branch instruction, we may still use the ALU to calculate the memory address for the load store, or similarly we will use the ALU to calculate the branch target address if it is a conditional branch instruction. Okay. So, these are some things we may need to use the ALU for, in addition to doing simple arithmetic and logic functions of the data that is given. So, note that we are trying to do a little bit of more work with the ALU, not just doing the arithmetic and logic functions required for an arithmetic logic instruction, but also using the same ALU for calculating addresses wherever we need them. So, when we look at load store kind of instructions, remember that we need to access data memory. So, we need to have a mechanism by which we are able to access the data memory when a load or store instruction is encountered. And then when it comes to the jump instructions, they are the conditional instructions, either we will have to jump to the target address, and if you are not jumping to the target address, you need to go to the next sequential address. So, the program counter therefore will have to be either updated with the target address. Remember, we need now a mechanism to calculate the target address, which may come first, for which you could either use the ALU or we need to have a separate unit to do that. Otherwise, we need to do PC equal to PC plus 4. We need to add 4 here. The reason we are adding 4 here is that we are assuming that each instruction consists of 4 bytes. So, the addresses of each instruction therefore will go in units of 4. Okay. So, we say that the PC, in order to point to the next instruction, you need to add 4, a value of 4 to it, so it points to the next instruction. So, this is what we do by saying PC equal to PC plus 4. Okay. So, now in order to do this, okay, let us take a look at what will be the kind of circuitry we will require. So, we are just going to build this starting from a rough sketch of what we would likely require. Okay. So, let us start with this first. What is our first step? We said we needed a program counter which will point to the instruction memory. So, we need a program counter, we need an instruction memory. Okay. So, these two units blocks we have. Now, the input to this instruction memory will be the value which comes from the PC, which is the address. Okay. So, once the address is given, the instruction can be obtained from that address. Okay. So, this part is simple, fetching of the instruction is simple once you give the address. Now, when the instruction comes here, now from the instruction, look at what all we will need. There will be different register values which will be specified in the instruction. So, from the instruction, we need to take out the different register numbers. So, this will be used to access the register file. Okay. And from the register file, we will get data out which will be given to the execution unit, the ALU, okay, for doing the arithmetic or logical operations. And we will also use the same ALU if we want to calculate the memory address for a load or store operation. So, if it was let us look at it step by step. Suppose it was only a ALU instruction. So, what do we do then? The output of this ALU has to be stored back in a register. Okay. So, we need a path from the output of the ALU to the register file, so that you store the value back. Otherwise, if it is a load or a store kind of an instruction, then the ALU will be used to calculate the address which has to be given to the data memory. So, we will assume now that the instruction memory and the data memory are separate pieces of memory, and the address will be specified from here, and if it is a store operation, the data to be stored would also be specified along with the instruction. So, that information has to be brought out, and then this has to be given to the data memory. So, it is a load instruction, the address would be specified, the data will be obtained which will have to be stored back in the register. If it is a store instruction, the address and the data to be stored would be given and it will be stored in the data memory. Okay. So, this is what we will require for the ALU kind of instructions and the arithmetic logic instructions and the memory instructions. Now coming to our PC part. Now remember, what did we do with respect to the PC? We either add 4 to it. So I am putting a separate add unit here, which will just do the job of adding a 4, or I may have to find the effective address, which may come from the instruction, jump to a particular location. I am assuming that that location will come from the instruction. So that value is added to the PC value. Now normally the jump values we specify are relative to the program counter. That is, you add that value to the program counter to arrive at the effective address. So the PC value that you have already added 4 to it, you are ready to execute the next instruction. We either take that value, or we will add this new value here, this relative address that is specified, add the 2 values, and then that value has to be stored into the PC. Okay, this is what we would roughly need to do. Now is this the correct actual picture that the circuit that we can use? The answer actually is no, because you can't just join up wires like this the way we showed. For our understanding purposes, we just said either this value has to go to the PC or this value has to go to the PC. Similarly, if we looked at where we said that the data will be stored back into the registers, the data was either coming from the ALU or it was coming from the data memory. Okay. Similarly, over here also we have some data which is being given directly from the instruction, or it may come through the registers. Okay. So these are different options we have. So what do you do in these cases when you really actually have to either take data from one path or another path? What we do is we use multiplexers. Okay. Remember what a multiplexer is. It is something which will choose one out of many. So that is what we need to do. We have multiple options here and we need to choose one out of these options. So what we actually will do is not join them up like this, but replace it with a multiplexer. Now this picture you can see has got a little more detail in it. Okay. So what I have added is I have added these multiplexers. So look at wherever we were just adding up, just tying things together, we put a multiplexer. You can see that we have a multiplexer over here. Now what is the purpose of this multiplexer? It will either choose this value which is coming from the PC plus 4, which means you are going to access the next sequential instruction, or the value which is coming after adding the target address or the target offset. Okay. We are assuming that the offset is specified in the instruction. So the offset will be added to this PC and that value will be fed over here, and one of these two will be selected and given as the input to the PC. Now how do I select one of these? I need some control information to select the correct value from the multiplexer. Now how do I generate that control information? Obviously I need some kind of a control unit which will help me to decide based on the instruction type what I need to do in order to select something over here. Okay. So this is what we will do. So you can see that we are adding more stuff here. So now we see we added one control unit here, we added a few multiplexers, and we are also adding some additional logic. I will just come to explain what this additional logic is required for. So that completed this part. Now let us look at which are the other places where we have a multiplexer. Now look at this portion here. So this portion here also we have a multiplexer, because the data that is to be stored back in the register may either come from the ALU itself or may come from the data memory. So you can see that there is a path from here to the MUX and then from here to the MUX, and there is one more input that is given here, which is the control to the multiplexer. Again this control input you can see is coming from the control unit. Okay. So you can see that there is a lot of control information that we need to generate. Okay. And if you look at the output of the multiplexer, the output of the multiplexer is now fed back to the as data to one of the registers that need to be stored. Okay. Now where will this control information actually come from? How will the control decide? Again you can see that information also has to be decided based on the instruction that is to be executed. So instruction information will also have to be fed into the control unit. Okay. So you can see that using a control unit and with the help of all these multiplexers and so on, and with logic you can have a complete path that can be designed. So we will stop now, take a small break and then come back and look at some of these details. Welcome back after the break. So we were just looking at how the control unit has to be designed. So we saw that there are different pieces that are required, and we are just looking at how these different pieces can be put together and how we need to design this kind of a control unit which will take care of actuating different parts of this entire system at the correct time, so that we are able to get the required operation. So how do we actually go about doing this? So to do that, obviously this involves some logic design. So we look at little bit of our logic design basics. We will just brush up some of our logic design basics so that we know exactly what we need to do. So remember, that information typically is coded in binary. A low voltage is 0, high voltage is 1, and we will normally use one wire per bit. So, when we are showing something as a single wire, it indicates that there is one bit of data that is being sent on that, and multiple data or multiple bit data will be encoded on multi-wire buses. Okay. So, this is a term that we have used earlier. A bus basically is a set of wires. Okay. So, when you have a data which consists of many bits, then we use typically a bus to indicate that. And then of course, we will use combinational elements and sequential elements. Combinational elements, they will operate on data and the output is a function of the input. So, you will have some using the basic gates, you will be able to generate this kind of a circuitry, and then we will use state elements or sequential elements for storing information. So, your design will be a combination of these factors. And when it comes to sequential elements, this is just an important thing that we need to remember. So, for instance, if you are storing data in a register, so we use a clock signal to determine when to update the stored value. So, typically we will have a clock signal that is specified, and then it is with respect to this clock signal that the timing of when exactly information is stored will be determined. And we will use edge triggered clocks, that the edge of the clock, that is when it goes from either low to high or high to low. So, that edge will be used for determining when the actual update takes place. So, we will assume for instance that the update takes place when the clock changes from 0 to a 1. So, if I have a D flip flop, when the clock changes from 0 to 1, the value which is there in the D input will go to the output queue. So, you can see what is happening here. So, even if the D value changes in between, until the clock input changes, right, from low to high, you can see that the output queue will remain at the same value. The D value here, whatever value was here, that value will be the one that is stored in the queue inside, that will be available at the output here. And only when the next clock occurs, you can see that this change here will be reflected. Okay, you can see the same thing happening here. So, this is something we already know, just to brush up this important concept. So, when you have sequential elements with write control, okay, remember that when you want to write data, so when you have a write control, we are now adding one more control element here. So, that is what we say is only when the write signal is at a particular value, you will allow the write to take place or the data to be actually stored in the register. So, in this example, for instance, you are assuming that only that the updates will happen only when the write control input is 1 and when the clock edge occurs. So, I am going to look for both the clock edge and the write value to be 1 for the output to be reflected correctly. So, look at what is happening here. So, initial value here, whatever value D is here, that is stored as soon as the edge occurs. Okay, that value has been stored here. Remember, the write signal is also high, so that value gets stored here. Now, when the next clock edge occurs, the write signal is low. If the write signal is low when the clock edge occurs, there will be no change in the output because the value will not be stored here. The value will be stored only when the write signal is high and the clock edge occurs. So, you can see that happens in the next clock cycle. Okay. So, this is typically what we do. You can see why we are bringing in these controls. So, you are basically saying that if I want an update to take place, I will put a control signal which will govern when that update will take place, not just based on the clock alone. Okay. So, you can see that when we need different control signals to be generated, those control signals will be used for these kind of purposes. So, we will use them as control signals for the various registers or for the various functional units that we are using. And coming to the clocking methodology, whenever we are designing sequential elements, we need to worry about how the clocking actually gets done. So, if you look at how the clocking gets done, you can see that the either we can use the edge of the clock or we can use the level of the clock. Typically, we use the edge of the clock because that gives us better control, and the longest delay, okay, is what would determine the clock period. Now, this is an important aspect to remember. That is, for instance, let us say you had some storage element here which is storing some state, and then there is a combinational logic which works on this output of this particular state. This state element 2 now will store the output of this combinational logic. You can also have a feedback coming back from this. Okay. Now, the cycle, the period of your clock will have to be such that, now if I want this entire operation to take place in one clock cycle, so the whatever will be the time delay for this combinational logic, that should be the period of my clock cycle. Okay, assuming that this whole thing takes place in a single clock cycle. Of course, we will look at other designs where if this takes too much time, we can also have multiple clock cycles to that. But to start with, assume that if I am designing my circuit as one state element, then some combinational logic, then a state element, then a combinational logic and so on. Typically, whichever combinational logic takes the longest amount of time, you will fix your clock period as equal to that longest amount of time. Okay. So, this is one factor that we normally use. Okay. So, keeping all these things in mind, let us look at how a data path can actually be built now. Okay. So, we said we have kind of indicated a basic structure. So, now we will look at in that basic structure how exactly the data path will work. Okay. Okay. So, what do I mean by this data path, this term data path that I am using? So, data path essentially consists of the various elements that process the data and the addresses in the CPU. Okay. So, which means we are talking about how the registers, the ALUs, muxes, memories, all these things are connected together. Okay. So, let us look at this data path for the simple architecture that we are looking at. So, if you look at this instruction fetch, let's start stage by stage. So, let us start with the instruction fetch. So, what does the instruction fetch data path consist of? Remember, this is what we already saw. So, this program counter here. So, we just said there is a PC. Now, how big is this PC? That has to be determined, right? So, if you assume that our instructions are all 32-bit wide instructions, we will also assume that the addresses that we are specifying are 2 to the power of 32 addresses that can be there in the instruction memory. So, now then the PC therefore now will become a 32-bit register. So, the width of the PC will give you how much of instruction memory can be accessed. So, if I assume a 32-bit register, up to 2 power 32 addresses can be accessed here. Okay. So, let us assume that. So, this path that I am showing here, okay, will actually be a 32-bit value which goes as the read address to the instruction memory. Okay. And then remember what we have the PC address going here, a value of 4 has to be added to it in order to get the next sequential address. So, increment by 4 for next instruction is done by this. Okay. So, this would give you the data path for the instruction fetch. Okay. Now, let us look at different type of instructions and that is the arithmetic and logic instructions, and look at what is required in the registers for doing that. So, when we want to handle registers, remember we have something called a register file that will be used. So, this will be our register file. Now, when you have a register file, you have to specify, let us say for instance, we are looking at a 3 operand instruction, that is 2 operands are specified as the read operands. So, which means 2 registers will have to be read, and then the output will have to be written to a separate register. Okay. So, you will specify 3 different register values. So, if you take for instance an R format instruction which has 3 register values specified. So, from the instruction you can see that I will get 3 register values which I will get. 2 of them will correspond to the input registers. So, read register 1, read register 2, and another will correspond to the write register. Now, when do I read and when do I write? So, obviously I need to have a control signal which will tell me when the write has to be done. So, you will have a control signal for that. And then if you are writing to the register, you need to specify which register you are writing to and what is the data that needs to be written. So, you will have to specify the data which has to come in over here. Okay. So, this is something that needs to be done. And if it is a read, there are 2, remember now we said that there will be 2 pieces of data that are read. So, there will be 2 data paths which are coming out from the register file. So, you can see that the register file will consist of all these elements and the control required to generate all these elements correctly. Similarly, if you look at the ALU will require 2 inputs which are coming in, and then the result of the ALU will have to be stored somewhere, and what operation actually needs to be done also has to be specified. In addition to this, when an ALU operation takes place, certain conditions may be generated. For instance, you may want to check whether the output of the ALU is 0 or whether a carry has been generated when an addition is happening. You may want to do some of these things. In those cases, we will have these different control signals that are generated. So, that will be specified over here. So, this is for a simple R format instruction. You can see that these will be the pieces of information we need. Now, if you look at a load store instruction, remember what we need to do for a load store. We need to read the register operands and calculate the address using a 16-bit offset, let us say. So, what do I mean by 16-bit offset? That is, all I am saying is I will specify an offset of 16 bits in my instruction, and that will have to be added to some register value in order to calculate the actual address. Okay. So, if a 16-bit offset is specified, now how do I add the 16-bit offset to the register value? We are assuming that all our registers give you 32-bit values. So, a 32-bit value is available and I have a 16-bit offset here. So, how do I add the 16-bit number to the 32-bit number? I will do what is called as sign extension. Once I do sign extension, that is convert my 16-bit number into a 32-bit number by doing sign extension, and then I can use the same ALU itself for doing the addition. Okay. So, if it is a load operation, you will read the memory and update the register. If it is a store operation, you will write register value to memory. So, the 2 pieces that we require for doing this therefore are, with respect to the data memory unit, we need to be able to specify whether it is a memory read operation or whether it is a memory write operation. So, these 2 control signals have to be generated, and we need to have a path for specifying the address, the write data and the read data. And we also need an additional sign extension unit which will convert a 16-bit number to a 32-bit number. Okay, these are things we require for handling a load or a store instruction. Now, it is a branch instruction. What are the things we need now? You will have to read register operands. You may have to compare operands in order to find out. So, for instance, we said we want to find out a branch if it is equal. So, branch equal indicates that I will have to read two operands, find if the two are equal, and if the two are equal, then I will do a branch. Now, how do I check two values read from a register are equal? Very simple. You do a simple subtract operation, check whether the output is 0. So, I will use the ALU, do a subtraction and check for a 0 output. Okay, this is what I will require for doing the comparison. Coming to the target address calculation part, again you may have to sign extend the displacement offset that is specified, okay, and then maybe shift left 2 places for a word displacement and add the value to the PC plus 4 that you have already calculated. Okay, this is what you will be required. So, what do I require for this? So, you will have data coming in from the registers, okay, which will have to be subtracted. So, the correct ALU operation has to be specified here, and the 0 check that we talked about, okay, that will now go to the control logic to determine whether you need to branch or not. Okay, so, this will go to the branch control logic, and we need this adder here which will be used to either add this offset that is coming from here. Now, where will the offset come from? It will come from the instruction itself. If it is coming from the instruction, I will do a sign extension, okay, and then get a 32-bit value here which you shift left by 2 and then add it to the PC plus 4, and therefore, you will get the branch target. Okay. So, you can see therefore, that by putting all these different additional pieces that you require for each type of instruction, you can kind of generate the required logic. Okay. So, putting all these things together, I will just give you a picture of what the full data path will look like. We will look at details of how this is actually constructed later, but this is what a full data path would look like, putting all those pieces that we just looked at together. Okay. And of course, we will have to add a control unit to this which will be used to control the various factors. Okay. So, what we have covered today is basically an overview of what goes into the design of a control unit. So, how do I decide that this is what I require for my control? So, once I have decided that, then using your basics of logic design, you can go ahead and design the control circuitry. Okay. So, to summarize, these are the points we have looked at. We have looked at designing a simple control unit for a simple set of instructions, and specifically we have looked at how the data path needs to be designed, how the multiplexers are used, and the need for multiplexers, and then of course we have looked at a little bit in terms of how the control signals have to be generated from the instruction. Details of this we will look at later. Okay. Questions to review the contents of today. Question number 1, what are the steps required for execution of an instruction? Question number 2, what is meant by data path? Question number 3, when are multiplexers used in a data path? Question number 4, show the functional units involved in A store instruction, B an add instruction. Question number 5, what would be the logic required for a jump instruction? Thank you.